Alright, let's continue. Let me open the table of content first. Okay. We are still in chapter 28. Previously we take a look until section 28.6 here, a file attempt just using load or store. Now let's take a look at this 28.7, building spin lock with test and set. Let me open that. Wait. Okay. Hopefully my internet connection is not down. Okay. Evaluating log. Controlling interrupt. Right. Using spin weight here, which can cause some problem. File uptime, load and store. If I remember correctly, yeah, this is the problem. Sometimes we might have interrupt from the hardware, so alt thread set the flag to 1. We cannot provide the mutual exclusion using this mechanism, load and store. Okay, now let's read this. Building working spin lock with test and set. Because disabling interrupts does not work on multiple processors, right? If I remember correctly, disabling interrupt only possible on one processor, something like that. And because simple approach using load and store as shown above don't work, system designer start to invent hardware support for locking. Oh, working spin lock with test and set. Okay, hardware support. Interesting. The earliest multiprocessor system, such as the Burroughs B5000, I'm not sure how to pronounce this. Burroughs? Yeah, I probably pronounced that wrong. But anyway, this B5000 in the early 1960s had such support. Today all systems provide this type of support even for single CPU system. The simplest bit of hardware support to understand is known as a test and set or atomic exchange. Oh, the simplest bit of hardware support to understand is known as a test and set or atomic exchange instruction. Okay, let me read this footnote first. Its architecture that support test and set calls it by a different name. Okay, calls it by different name on SPARC, SPARC. It is called the load/store unsigned byte instruction, LD stub. On x86, it is the lock version of the atomic exchange. Oh, XC HG, the log version of the atomic exchange. Okay, I am still have no idea what this atomic exchange mean. Just something to keep in mind. In test and set. Okay, wait a minute. We to find what the test and set instruction does via the following C code snippet. Okay, this one test and set. This is the, what is it called? Parameter, I guess. Fetch out value at old PTR. This one. Okay. Store new into old PTR. Okay. Wait a minute. Is this passing us a normal value or a pointer? Oh, wait. Right, we assign this. Okay. Alright. So this is the normal value. And we put the normal value there as the new value, maybe something like that, and then we return the odd value here. Okay. Oh yeah, this is this aside is a lot. Let's read this after we read this section first. Okay. Alright. What the test and set instruction does is as follows. It returns the old value point to by the old PTR, right? And simultaneously update set value to new. The key, of course, is that the sequence of operation is performed atomically. So all or nothing, if I remember correctly. The reason it is called test and set is that it enables you to test the old value, which is what is returned, while simultaneously setting the memory location to a new value. Okay, test the old value, the one that we return maybe, while simultaneously setting the memory location to a new value. As it turns out, this slightly more powerful instruction is enough to put a simple spin lock, as we now examine in figure 28.3. Okay, this slightly more powerful instruction is enough to put a simple spin lock, as we examine this. We now examine in figure 28.3, or better yet, figure it out first yourself. Okay, figure 28.3, a simple spin lock using test and set. Okay, we have this struct with the member flag here. Okay, init. Okay, initialize the flag. 0 is available, 1 is locked. Okay, okay. We are still using spin wait here. Alright. And then unlock. test and set. Assuming this is, what is it called? Atomic, right? Atomically. Okay. Let's make sure we understand why this lock works. Imagine first the case where a thread calls lock and no other thread currently holds the lock. Thus flag should be 0, right? When the thread calls test and set, flag 1, okay. The routine will return the odd value of flag, it is 0, thus the calling thread, it is testing the value of flag, will not get caught spinning in the while loop and will acquire the lock. This one, when we test this scenario, right? The return of this is 0, it is not equal to 1. That's why we exit, I guess. Okay, the condition is not true. Okay. Wait a minute, where is it? Will not get caught spinning in the while loop and will acquire the lock. The thread will also atomically set the value to 1, thus indicating that the lock is now held. When the thread is finished with its critical section, it calls unlock to set the flag back to 0. Okay, again the important part here is atomically. The second case we can imagine arise when one thread already has the lock held, that is flag is 1. In this case, this thread will call lock and then call test and set flag 1 as well. Oh, okay. One thread already has the lock, and then a new thread, I guess, call this function again, test and set as well. This time test and set will return the odd value at flag, which is 1, right, from the previous thread here. Because the lock is held, while simultaneously setting it to 1 again. As long as the lock is held by another thread, test and set will repeatedly return 1. And thus this thread will spin and spin until the lock is finally released. Again, this mechanism here. So this while loop will keep going until the lock has been released, or at least until this test and set return 0, something like that. This one, return the odd value. Okay, when the flag is finally set to 0 by some other thread, this thread will call test and set again, which will now return 0 while atomically setting the value to 1 and thus acquire the lock and enter the critical section. Okay, by making put the test of the old log value and set of the new value a single atomic operation, we ensure that only one thread acquires the lock. And that's how to build a working mutual exclusion primitive. You may also now understand why this type of lock is usually referred to as a spin lock. Okay, it is the simplest type of lock to build and simply spins using CPU cycles until the lock becomes available. To work correctly on a single processor, it requires a preemptive scheduler. That is one that will interrupt a thread via a timer in order to run a different thread from time to time. Without preemption, spin lock don't make much sense on a single CPU, as a thread spinning on a CPU will never relinquish it. Preemptive. Okay, let me check. Wait, not that one. Okay, that doesn't really tell anything. Serving or intended to preempt or forestall something, especially to prevent attack by discipline. What is preempt? Okay. One that will interrupt a thread via a timer in order to run a different thread. In order to run a different thread from time to time. Okay, basically something like an interrupt timer, maybe something like that. And again, without preemption, a thread spinning on a CPU will never relinquish it. Okay, let me read the aside. This one, okay. Aside Dekkers and Peterson algorithm, in the 1960s, Dijkstra posed the concurrency problem to his friend, and one of them, a mathematician named Theodorus Joseph Dekker, came up with a solution. Okay, unlike the solution we discuss here, with use special hardware interaction and even operating system support, Dekker's algorithm uses just load and store, assuming they are atomic with respect to each other, which was true on early hardware. Which was true on early hardware. Yeah, I'm kind of curious. What kind of atomicity that early hardware has, I guess. Dekker's approach was later refined by Peterson. Once again, just load and store are used, and the idea is to ensure that two threads never enter a critical section at the same time. Yeah, I mean, the book mentioned early hardware, right? So I assume maybe there is some difference how the early hardware behave compared to the current hardware. maybe something like that. So yeah, and is this Peterson algorithm also using the same hardware as Decker or not? Okay, once again, just load and store are used, and the idea is to ensure that two threads never enter a critical section at the same time. Here is Peterson algorithm for two threads. See if you can understand the code. What are the flag and turn variable used for? Okay, flag and turn indicate you intend to hold the lock with flag. Whose turn is it? That 0 or 1? Oh. Okay. So we set the flag, I think put flag to 0, maybe something like that. Okay, whose turn is it? Self is the thread ID of the color. Make it other thread's turn. Okay. Alright. Well, flag and turn. Oh, wait a minute. I assume this is one condition. Yeah, I kind of forgot the sequence here. Is this have the high priority over this? Maybe. Let me check. What is it called? Sequence point, maybe. I mean, can we check this condition, right? And this one, the order is kind of confusing. Is it called sequence point or order of evaluation? Maybe that's the thing. Maybe not. But yeah, I mean, if I remember correctly, there's an order to prioritize in the expression. I usually put bracket to make this easier to understand, I guess. Either doing this first or this first. Right. Spin with, well, it's not your turn. Okay. So I assume this one is the condition. If turn equal 1 negative self, first check this, I guess. If the flag set to 1, right, for one negative self, right, we check this condition. If turn equal one negative self, I'm following this pattern, I guess. But then again, turn is one negative self. Like what? And then this is one negative self too. Interesting. I mean, why didn't we change this to turn? Or maybe, oh, wait a minute. Yeah. Is self gonna keep changing? I am not sure. Self is the thread ID of color. Oh. Self is the thread ID of color. So maybe self in here might change depending on the thread we're currently using. Like, I mean, again, looking at the interrupt. Where is it? The interrupt scenario. This one, I guess. Suddenly we have interrupt, right? So we might change the self here when having interrupt. Maybe that's why we didn't use this turn variable and use this instead. And if the previous turn, this one, is the same as the current turn after the interrupt, maybe something like that, we will keep spinning, I guess. Simply undo your intent. Okay. This one. Yeah, I'm kind of curious about the hardware here. What is the difference between the early hardware and the current hardware? Like, what kind of hardware the Decker's algorithm here use? And maybe what kind of Peterson algorithm use? So yeah, I'm still not sure about that. For some reason, developing log that work without special hardware support become alterates for a while, giving theory types a lot of problems to work on. Oh, of course, this line of work become quite useless when people realize it is much easier to assume a little hardware support. And indeed, that support had been around from the earliest days of multi-processing. Further, algorithms like the ones above don't work on modern hardware. See? Don't work on modern hardware. So there is some difference there. The way to relax Memory consistency model. Oh, okay. Relax memory consistency model. Maybe because of the virtual memory stuff. So it's not really consistent. I mean, there's a randomizer, if I remember correctly, for security purpose. I think it is during maybe this one, the Linux virtual memory system, if you want to revisit that. Some kind of randomizer for the virtual address space. Okay, maybe that's why this algorithm didn't work on modern hardware, thus making them even less useful than they were before. Yet more research will really get to the dustbin of history. Okay. Alright. Tip. Think about concurrency as a malicious scheduler. From this example, you might get a sense of the approach you need to take to understand concurrent execution. What you should try to do is to pretend you are a malicious scheduler. Okay. Understand concurrent execution. What you should try to do is to pretend you are a malicious scheduler, one that interrupts thread at the most inopportune of time in order to foil their feeble attempts at building synchronization primitive. What a mean scheduler you are. Yeah, we are a mean scheduler. Okay. Although the exact sequence of interrupt may be improbable, it is possible. And that is all we need to demonstrate that a particular approach does not work. It can be useful to think maliciously, at least sometimes. Okay. Think about concurrency as malicious scheduler. That is an interesting concept, I guess. Okay. Yeah, let's continue evaluating spin logs. Given our basic spin log, we can now evaluate how effective it is our previously described X. The most important aspect of a log is correctness. Does it provide mutual exclusion? The answer here is yes. The spin log only allows a single thread to enter the critical section at a time. Thus we have a correct log. The next axis is fairness. How fair is a spin log to a waiting thread? Can you guarantee that a waiting thread will ever enter the critical section? A waiting thread will ever enter the critical section. The answer here, unfortunately, is bad news. Spin log don't provide any fairness guarantees. Indeed, a thread spinning may spin forever under contention. Simple spin log, as discussed thus far, are not fair and may lead to starvation. Right, basically another thread didn't get the chance to enter the critical section. That's what it means. That's what starvation in here means. The final axis is performance. What are the costs of using a spin lock? To analyze this more carefully, we suggest thinking about a few different cases. In the first, imagine threads competing for the lock on a single processor. In the second, consider thread spread out across many CPUs. For spin locks, in the single CPU case, performance overhead can be quite painful. Okay, imagine the case where the thread holding the lock is preempt within a critical section. The scheduler might then run every other thread. Imagine there are n-1 others, each of which tries to acquire the lock, right? In this case, each of those threads will spin for the duration of time slice before giving up the CPU, a waste of CPU cycle. Okay, yeah, maybe what is it called? Yeah, maybe it's the same like the spin weight in general, I guess. Basically, taking up the CPU until the interrupt begin. Maybe. However, on multiple CPUs, spin lock works reasonably well if the number of threads roughly equal the number of CPUs. The thinking goes as follows. Imagine thread A on CPU 1 and thread B on CPU 2, both contending for a lock. If thread A CPU 1 grabs the lock and then thread B tries to, B will spin on CPU 2 instead of CPU 1, right? However, presumably the critical section is short, and too soon the lock becomes available and is acquired by thread B. Spinning to wait for a lock held on another processor doesn't waste many cycles in this case, and thus can be effective. Presumably the critical section is short, and too soon the lock becomes available and is acquired by thread B. Spinning to wait for a head on another processor doesn't waste many cycles in this case, and thus can be effective. Okay. If the critical section is short, if it is not short, then maybe we will have the same problem too, like waste of CPU cycle, maybe. Okay, and then compare and swap. Another hardware primitive that some systems provide is known as the compare and swap instruction. It is called on SPARC, SPARC, for example, or compare and exchange as it called on x86. The C pseudocode for this single instruction is found in figure 28.4. 28.4, this one, compare and swap. Okay, this is the pointer, normal value, the reference here. Okay. If the original equal expected, okay, we put the new value in the pointer and then return to original. Okay, so if it is not expected, we just return the original value without changing the value in the pointer. Okay, maybe it's something like that. The basic idea is for compare and swap to test whether the value at the address specified by PTR is equal to expected. If so, update the memory location point to by PTR with the new value. Okay. Whether the value at the address specified by PTR is equal to expected. If so, update the memory location point to by PTR with the new value. If not, do nothing. Okay. Update the memory location point to by PTR with the new value. If not, do nothing. In either case, return the original value at that memory location, thus allowing the code calling compare and swap to know whether it succeeds or not. With the compare and swap instruction, we can put a log in a manner quite similar to that with test and set. For example, we could just replace the log routine above with the following. Okay. With the compare and swap instruction, we can put the log in a manner quite similar to that with test and set. A log in a manner quite similar to that with test and set. Could just replace log routine above with the following. This one. Okay. The rest of the code is the same as the test and set example above. This code works quite similarly. It simply checks if the flag is 0, and if so, atomically swaps in a 1, thus acquiring the log. The rest of the code is the same as the test and set example above. This code works quite similarly. It simply checks if the flag is 0, if so, atomically swap in a 1, thus acquiring the log. Threads that try to acquire the log where it is held will get stuck spinning until the log is finally released. Threads that try to acquire the log where it is held will get stuck spinning until the log is finally released. If you want to see how to really make a C-callable x86 version of compare and swap, the code sequence from this reference might be useful. Okay. Finally, as you might have sensed, compare and swap is a more powerful instruction than test and set. Okay, wait a minute. Let me check. Okay. Oh, because we have the expected value there, I guess. Right. So we didn't just change the value here. Okay. And expected is 0. Oh. Alright. Okay. We will make some use of this power in the future when we briefly delve into topics such as lock-free synchronization. Okay, is a more powerful instruction than test and set. I am still not sure. How powerful is this? I think the condition here. Right. I mean, if I understand correctly, the difference is those expected value. So basically, instead of just replacing this memory, this value, right? We check whether the original value the same as expected value, and in this case, this is the original value from the log flag to the expected value, it is 0. So if the original is not 0, we do nothing, I guess. Maybe that is what makes this more powerful instruction than test and set. But yeah, I'm still not sure yet. Flag 0, if so, atomically swap in a 1, thus acquiring the lock. We will make use of this power in the future when we briefly delve into the topics such as lock-free synchronization. However, if we just build a simple spin lock with it, its behavior is identical to the spin lock we analyzed above. Yes, if we just put a simple spin lock with it, its behavior is identical to the spin lock we analyzed above. Okay, load, link, and store conditioner. Okay. How many? Okay. Alright. There's load, link, and store conditioner. Fetch and add. Too much spinning. Okay, simple approach. Use quiz. Okay. Two-phase lock. You know what? Let's continue this. Oh, hello, Twitch. You should stream on Twitch plus YouTube. Well, I may consider that, but for now I'm just using YouTube for simplicity. Okay. I think let's continue this on the next session. Load, link, and store conditioner. Yeah, we have, I guess, a lot to read here. Alright, so that's it for now. Thank you for watching and see you next time. Bye bye.